worked. Nice. Cool. And then we've still, I think, got a few people that will trickle in the next few minutes, but just going to get started for the sake of time. So from my side, or I guess general agenda for today is rather simple, like they have been the last few lectures. I just have really quick updates on my side, and then I'm going to hand it over to Jamshid, and he's going to give his presentation / lecture on generalized dynamical systems, which is a really exciting topic. So I hope you are all excited, glad to be joining us today. And then, yeah, we'll wrap up at the end with the homework assignment and just a reminder for the next session. So yeah, pretty straightforward. So the updates on my end quickly, I just wanted to give a shout out to Joe's and Rudy for presenting in the Hack and Share on Tuesday. They, for a quick reminder for the other folks, is that Hack and Share sessions are a time where we can take problem solving in crypto or with in DeFi specifically from applying our own lens, so from our own expertise, from whichever academic background we come from, or professional background we have, and kind of applying that lens to a concept in AMMs that we have identified through our research or through these lectures, just to kind of help give other people perspective on how we're thinking about these problems. And it's usually really exciting to see how other fields can approach the same topic, but from different angles. So Rudy gave us some perspective on thermodynamics, and then Joe's was talking about how he was thinking black swan events could be protected against in crypto from an economics perspective. So really interesting conversation, and a lot of it has continued in the Discord too. So read through that if you feel like you missed out. And yeah, then the last, of course, a reminder oh yeah, good point, Henrik. I wanted to mention that too. There's been a few people with some bugs that have run into the same bug, trying to install cadCAD on their Windows computers, or going on through the onboarding process on the Windows computers. So I think we may have found a solution. We may have found a solution, but if you did run into a problem and still haven't figured it out, definitely reach out to me or others in the Discord channel, and we can figure something out.
Peter, Henrik here. I think it's more sort of like, as this becomes more complex, I mean, I have a nice Windows setup, but the more people I speak to, Windows is really not hot in this space anymore. So it's been sort of for 6 months, like maybe it's time for Mac, but is this going to be so complicated modeling when we get to like 3 weeks from now that I might as well use this opportunity to shift to a Mac, because it's just going to crash even more with Windows? Well, I'm guessing you guys have religious opinions about it, but
I just say from what I've heard, aside from this issue with the setup, which is frustrating because it's literally step 0. But aside from that, I haven't heard many issues depending on operating systems, but I'm not sure if others have comments that have done more intense modeling on their devices. I kind of think that Windows should be okay once you get past that first hurdle.
I can see Rudy says Linux. I guess that's beyond my bandwidth.
Yeah, that's another learning curve. But yeah, I think
thanks.
Probably good. Yeah, no problem. Cool. So then, besides the cadCAD issue, that is it for the updates. And then just a reminder for everyone to not be afraid to ask questions, because we're all, like Kirti was just mentioning, we're all coming from different backgrounds and have different definitions for words and Just think about problems differently. So if something's confusing, better to ask it and get caught up before you get too far behind. So with that, I will pass it over to Jamshid. And yeah, the floor is yours.
Thanks. Let me go ahead and quickly share screen. Everybody can see that title slide?
Yep.
All right. Great. Well, thanks everybody, and thanks Peter for the intro. So this is now going into the let's say, I guess we're kind of the third of the 6 types of sessions looking at the this engineering design process workflow that started out with a general overview of AMMs and the Hydra AMM in particular in session 1 with Chris, and moved into essentially system identification from the point of view of identifying what is the system that you're actually looking at from what Barlin gave us last week. And so what I'm going to do is to use this opportunity now to start building upon what you've seen. So it is really, it kind of has a natural fit to the next layer of, well, we set up what a system is, let's move forward from there, and then define a one particular formalization or abstraction that can be used later on to build the blueprint that we then take to a computer implementation. So next week with Barlin's comes back on deck to actually describe that blueprint, which we call a mathematical specification. And in the meantime, what I'll be doing today is to describe the step before that, which is generalized dynamical systems. So I'll start today just with an overview of the goals, kind of as we've been doing week to week, but what are sort of the expected goals upon finishing through the lecture itself. I'll go through just a very quick recap of the system definition along the lines of what you have done in last week's assignment. Then take a step and say, okay, why were we, or how would we want to formalize a system? Introduce one particular mechanic that we use at BlockScience in order to understand, in particular, how requirements can give us system properties that we can understand within a context called a generalized dynamical system. This is essentially the prerequisite for being able to build the blueprint that we would then be using in a mathematical specification and then take that to a computer implementation. I'll then dig into the cadCAD code of the Hydra simulations just to show one example of some of the features of the GDS that we had been describing before, just to give some familiarity with not just looking and stepping through some of the code, but also kind of identifying the different characteristics that make this up. So it's coming from 2 different angles, the abstract side and then from the code centric side, let's say. And then finally, in the GDS assignment, this will be, again, kind of like what you had in Barlin's assignment last week, specifically looking at your own system of interest and identifying those components that would make up the GDS representation for that system. So again, we're not looking for a high degree of mathematical abstraction or complexity here. It's really more about just the conceptual frameworks that we're building to create this workflow. That we're working through this engineering design process. Okay, so the goals for today, this lecture is really to understand the reason for formalizing the requirements of a system. This may seem obvious right from the beginning, or it may require a little bit more nuance to kind of tease out how and why would we do this. We'll contextualize that formalization within this engineering design workflow using generalized dynamical systems as the formalization. And in particular, there are things that are identifiable as components or building blocks of the GDS that are the way in which we then transcribe those relationships into a blueprint that we call a mathematical specification. Those are the states, how the states change, and user actions and their admissibility. There are other factors that will be coming in there, like things that may come in that are random, but we'll keep to sort of the building blocks that are identifiable from the higher level. We'll then examine the Hydra liquidity subsystem from that perspective of a GDS, and as mentioned, then as part of that assignment, start to prepare the idea of how to formalize taking this abstract framework, which is what the GDS is providing, and build the blueprint of the mathematical specification from that. Okay, so building upon what we saw last week, remember that we are able now to define a system by its context, what is inside versus outside of the system, by its interfaces, what comes into the system, what may leave the system, and the views, the different types of components that we're examining in the context and the interfaces from which we desire to look at it from that point of view. Just to note, of course, that when you are building the system, the next thing and the thing in the back of your mind, and this gets back to kind of the questions of business requirements, is this idea that the system is being designed to do something, to fulfill certain objectives or certain goals. And as you look into how the system is being defined, where you draw the box, those goals can shift or change depending upon the way in which those boxes are drawn. So changing the context can present, for example, additional or different system goals as you incorporate more or less into the system or subsystem of study. Changing the interfaces may not necessarily change the system goals, but will usually change their implementation as you've opened or closed, let's call them ports, into and out of the system itself. So just two things to note about as we're building this notion of what the system is and how we're going to start formalizing the system, first from a kind of a dynamical systems approach, and then into this blueprint. And once you've got that system definition, which you've all had a hand at trying over the last week's assignment, then the requirements of the system goals can be introduced. And it's the way in which these requirements are introduced in a formal setting that is essentially the segue between last week's information, last week's lecture, and today's. So it's again part of this design process workflow that, remember, in all the way back in stage 0 of everything, has been predicated upon stakeholders sitting down and saying, what do we want the system to do? So they're always lurking in the back of the environment, but when you're setting up a system to design, what you have done is built the box in which the system is going to be placed, and then on top of this, take those system goals and requirements and say, okay, given the fact that I have this context and these interfaces, or given the fact that I have a context and I want certain interfaces, how do I best reflect the design of that system, the system goals that the stakeholders have come up with? That's kind of this overarching thread. This will continue all the way through the rest of the workflow itself, all the way up to and including the computer implementation, using the reference implementation through cadCAD, and also a description on mechanism design. How do you choose certain features of the system which best reflect certain metrics that assess the system goals? So that's kind of the path forward from what we're doing today. Okay, so let's think about how we would move to formalizing a system itself. What does that entail from our point of view? Well, what we would like to be able to do is to place structure using these requirements, this idea of the system goals in our background, upon a system with an eye to the notion that the system is inherently dynamic. A static snapshot of a system itself, an unchanging system, doesn't really fulfill most, if not all, of the types of requirements that a system definition is encapsulating. And so it's this notion that the system evolves and changes over time that presents, in a sense, the challenge of how do we build requirements into the system in a structurally consistent fashion. One example, for example, would be Bitcoin. If we look at the Bitcoin network, the set of the addresses for transferring Bitcoin between isn't fixed in size, but can grow. And in fact, that can add a dimension as new addresses are added. And so one of the natural questions would be, when you're trying to think of a formal setting, you want to place something into the system such that the addresses can grow, how should addresses be added? This would be the underlying question of the connection between the design of the system and its underlying requirements. In the same way, the unspent transactions output, the UTXO, that set is not fixed in size, but changes as users perform different operations. Well, how should users perform operations? How should they impact the system? The system itself is up for design, and so the way the user interacts, the interfaces that the user is being provided with, should fulfill certain types of goals or preserve certain operation properties in that context. And so in general, to understand the entire stakeholder ecosystem, the user's taxonomy, the value flows that are coming from the business proposition at the system level allows you then to say, this is where these different components fit in a formal representation. And that representation should be something where the idea of changing something over time is performed in a consistent fashion. So that's in a nutshell, the reason why you would want to be formalizing components of the system to be implemented. It may sound obvious, and for most people who have a background in designing anything, this may seem sort of like a thing you just normally do. But it is important, I think, to be able to say, conditional upon the formal representation, how then do we select among the many different formalisms that can occur, the ones which best reflect this incorporation of these requirements and system goals into the engineering design. So remember, just a quick recap from last week, the types of requirements that we're thinking about in the back of our minds when we start to understand what we want to formalize. We have types of requirements such as operational, how well does the system serve users and under what conditions does it serve them? Functional requirements, what are the necessary tasks or actions that must be present in the system? Performance requirements, to what extent is the function that is being executed? What extent is that function's execution being delivered up to some standard? What's the quality of that execution? Design requirements, how will the system be built? What are the technical needs or substrate needs that are present? Derived requirements, this is now becoming a taxonomy then of high level versus lower level requirements. What requirements are primal in the sense of being higher level and what are derived? And finally, allocated requirements. How are higher level requirements themselves divided into one or more lower level requirements? And this becomes important when your system is very large. If you start to build different subsystems, you start to allocate different sub requirements from overarching business requirements, for example, at the top level. So this is just a recapitulation of the types of requirements that we've seen from last week. But again, this is the notion that, okay, what's the next step? How do we start building a framework within which we can actually define these different requirements in a consistent fashion for implementation? And this causes a trade-off to occur in formalization. Most of you who have had any experience, again, as before, have already seen and been confronted with this trade-off. The challenge is to represent potentially a very complex system requirements in such a way that you can do implementation to begin with, that it doesn't just remain a theoretical exercise. The goal then is to select among the many different alternatives of formal frameworks, of formal representations, something that in a way can be, I want to call it future-proof, but agnostic to the implementation framework in the sense that it can work with an implementation, one of many different implementation frameworks today, but also can be used as a way of guiding or signposting implementations in the future. So that's the trade-off. You need something which is general enough to be able to include large complex systems and the way that they change over time. But it has to be specific enough to allow the uncovering of the system's properties that the requirements are implying so that they can be formally verified during the implementation's process of verification. Because that's the way you get the matching. If you remember all the way back to the workflow that we have on the engineering design process, you want to make sure that you put in to the system, the implementation, what it is that you think you're doing, what it is that you think you've created. And so being able to do this requires this ability of seeing the forest for the trees. In other words, you want to be able to see the big picture while at the same time being specific enough to create an implementation that allows for verification. And so this is in many ways is a tricky trade-off to do. Sometimes it is more art than science to try and find a way around this without a formalization acting as a backdrop. And so once you have a formalization that meets this criteria, then you are able to leverage that in building what is essentially the computer blueprint for any implementation that meets a certain set of computational criteria, which we're going to get into in more detail as we move into the mathematical specification. And then finally, cadCAD, not as a specific code-based, Python-based implementation, but rather as an implementation framework within which the mathematical specification can be expressed. So it's a subtle distinction, perhaps, that we'll get to in not the next week, but in 2 weeks, describing how it is that we move from the blueprint that is created from the formalization we do today in a computer representation. Okay, so that's the lead into one such formal representation that provides us with the ability to have this complexity versus specificity trade-off. And this particular kind of representation is called generalized dynamical systems. To motivate this, I'm going to introduce a little bit of well, a few equations as representations. So don't take them as things that need to be derived. If you have never seen any of this before, don't worry. There's not a lot of formalism that is necessary. It's more about identifying the bits and pieces that, when you put it all together, allow you to assert certain properties of a system that changes over time. But I will use some of the mathematical notation. So if it's something you haven't seen before, of course, please stop me and then we can describe it in more detail, or you can bring it up in the session on Tuesday, for example. But hopefully what I've done here is to kind of meet in the middle. There's a little bit of this that if someone is well versed in dynamical systems analysis, they will have seen all of this before. And for those of you who have never seen it before, it will come across as very new, but hopefully there are other methods of explanation and presentation that are accompanying this equation-based approach that will help. Okay, so let's start with what for many of you might be something you've seen before, which is just how to model mathematically a dynamical system, a general dynamical system. A dynamical system itself is a representation of a system that evolves over time. That evolution may be entirely deterministic in the sense that when you have seen something that sufficiently summarizes the system, you can make a perfect one-to-one prediction of what is happening next. Or it can be subject to non-deterministic or random influences, which allow you to say, well, I know everything that I can know about the system. In particular, perhaps I know everything that's happening within its boundary, and I understand its context, but its interfaces are allowing randomness to come in. And that randomness that comes in can change what might happen in a way which is non-deterministic, so that I end up getting potentially, depending on how well I understand what's impacting this through these interfaces, potentially a probability distribution of possible outcomes. But irrespective of whether it is deterministic or random, what is happening is that there is a conditioning upon something that is acting as a sufficient statistic, so to speak, of the system at a particular point in time. And in the typical dynamical system, which I kind of use in quotes because there's such a plethora of different sub-applications and discipline-dependent methodologies, that there are many, many, many different ways of claiming one dynamical system is more typical than another. So with that grain of salt, let's use as our template a particular dynamical system that evolves a numerical state, we're going to call that capital X, over time t. And t, we'll discuss a little bit more detail what we mean by time in this particular case. And we do this according to some sort of a function, and this is f sub t, which itself can change over time, which allows us to say if the state was x at t minus 1, time t minus 1, that it is in time t, x sub t. And that's if we have discrete time where we can number the points themselves, yesterday, today, tomorrow, and so on. In a continuous time environment, we're usually not able to say it's exactly this amount. We're just going to say there's a change that occurs over a sufficiently small time interval. And if we call that sufficiently small time interval dt, then the small change in the state, dx of t, in parentheses now, is given as a function of the state of the system at time t. So these are two different representations, one discrete time and one continuous time, of a dynamical system. And the state itself is essentially being represented by numbers, or by a vector, or by a matrix of numbers typically. And of course, for a computer implementation, that's always true. There's always going to be something which you are representing by numbers. But we're going to be expanding from the abstract point of view what it is that we allow a state to be when we examine things from a generalized dynamical systems point of view. And that's the reason for the word generalized. It doesn't really add too much in terms of the complexity of changing things over time. It just provides a more formal framework for allowing the things that can change over time to be more general than simply a vector of numbers, for example. So it's a representation, a GDS, a generalized dynamical system, is a representation of a dynamical system that evolves. Instead of thinking of the state X as a series of numbers, think of it as a data record of some kind. And that data record has sufficient structure to enable it to be rendered as a sufficient statistic for the system as a whole. So of course that encapsulates numbers as with a typical dynamical system. It also incorporates things like relationships, for example, a database relationships or a graph or network structure. So you may have, for example, vertices and edges that themselves are encapsulated as a particular representation of a network at a point in time. And of course, eventually, when you get to a computer representation, that gets transcribed into numbers. But from the abstract level, you could say, well, the state of the system is a particular network. And by generalizing and lifting a little bit higher up, you can say, well, okay, we've got numbers, we've got relationships. In fact, we could think about the state as comprising objects. So abstract subspaces, things that are restrictions on other pieces of the system's architecture that themselves change over time. And this is the way in which the generalized dynamical system allows the ability to have these ever more abstract representations of the system's particular snapshot at a point in time to be consistently defined in how it changes. Because remember, that's the idea of having the dynamical system being the primal idea of how does the system change over time? How do I formally represent that? Well, once you have figured out what you need in order to be able to represent the system, its state, that then can inform you about how that state changes. So we're going to use some overload in the variable names. We're going to call a state within the GDS X once again, where it's now more general as an object. And time then proceeds in a discretized or continuous fashion. And I'll touch on this just a little bit more detail in a moment. And the evolution of the state, or the state transition, is now represented by some kind of a mapping, which we call f of t, which can change over time, and which may not be, strictly speaking, a function of numbers with a domain and a range, but may incorporate more general transitions. It may incorporate set transitions, set inclusion, or set difference, for example, as mutations over time. So this is the way in which we can build a more abstract framework while still retaining the flavor of what is changing from one point to the next. And just to give one bit of a flavor on the scaffolding underlying all of this, is you notice that the thing which we haven't really expanded upon or abstracted away from too much is time. We still are using this label, the subscript T, but I just wanted to give you the feeling that for many different types of dynamical systems, what we are referring to when we index things by time can be richer than one particular paradigm. So it doesn't necessarily have to be stuck into a continuous time paradigm, or you're stuck in a discrete time paradigm. You can move to different types of things that may be more natural for the phenomenon that ultimately you're attempting, or the system is attempting to model. So very few examples here. Again, many of you have probably seen much of this before, but just to put it into the notes so you have them in the slides. One representation of time, which is good for differential equations and updates that occur over very small time intervals, is continuous time, where time is a real number. Uniform discrete time is something we would say a tick of a clock, the seconds, the minutes, the hours, and the days, equal spaced partitions. This is the next natural way in which we would have a difference equation using discrete time. And I'll use this as the workhorse moving forward, just in the way of for labeling more than anything else. We're not doing any kind of mathematical analysis, but we're just going to use it as the label for the most part. There's also block time. Block time is when a block happens to have been packaged for its transactions, for example, and then arrives. It's a non-uniform, but at discrete points in time. It has an arrival at a particular tick, but those ticks are not necessarily evenly distributed. And that may or may not change how you feel the modeling transitions are framed vis-a-vis a discrete time environment, where in between a block update, nothing is necessarily taking place that you can estimate directly, but you may be able to find indirect methods of understanding what's happening. And if you unpackage a little bit what's happening inside a block, you end up with what might be called event sequence time. At BlockScience, we find that most of the systems that we are investigating are at the resolution or the fidelity of event sequences. So the things that are happening are occurring within blocks, but they are at what we use for most of the modeling techniques. We'll use them at continuous points in time. Sometimes we'll do discretization or set up a discrete system if it's more natural, but otherwise it's as if you have a continuous time system underneath, but these events are just coming whenever they're arriving. If you think about a random process, some sort of a Poisson process, things are just sort of popping into the environment. And the event then becomes, in a way, the most primal way to collect data, and that informs then how you want to label things from the dynamical systems point of view, because it influences which kind of framework you would feel, which kind of transition function you would feel most aptly reflects the way in which data is actually coming in the real world system, or the way that is being envisioned if you're designing something from scratch. Okay. I'll take a quick pause here and just ask if there are any questions. If I've missed a chat, certainly let me know. We'll take a quick breather here just to see if there's anything that strikes anyone as something they've already seen, not seen, anything new, or anything else I can explain better.
How do you model scenarios, specific scenarios? Are they unique events, or I don't know? I'm just thinking.
Excellent. No, that's a great question. So scenarios are actually in full generality, particularly when we're using cadCAD to assess them. They are actually ensembles of possibilities. So, for example, just one way of thinking about this might be that there is a scenario where you have a price oracle. A price is coming into your system that you think people are conditioning on, but you don't know necessarily what the value is. Instead, you build some kind, perhaps from data, perhaps from examining real prices and changes, you build a model of how that price is being generated. Perhaps it's coming from a stochastic process generator from a probability distribution. Perhaps there's a more complicated systems identification or a time series analysis or machine learning you've done. And that particular realization of each time that oracle gets a value is one scenario. It's the scenario of that particular value entering into your system, and then your system does something in response. And by generating many, many realizations, once you've created that model of the external processes, the stochastic processes that come in, you're able to generate an entire picture of all of the things that can transpire, given all of the different realizations from that stochastic process. And by doing this in such a way that you have some nice definitions of the properties of the stochastic process, you're generating what is called Monte Carlo analysis. And so you're generating ensembles of the realizations of the random influences that are coming in and examining the outputs, and then attempting to do some kind of inference on the basis of what you're seeing as output.
It's interesting.
Are we going to see in a later session how you parameterize different input events?
Yes.
Okay.
Yes, we are. We're going to examine one or two parameterizations of mechanisms and see how those mechanisms can be influenced by other sets of parameters that we fix. For example, I think in the HydraDX, one of the nice examples is trading order. When somebody decides to execute trades in a particular order, they decide to randomize between different assets that they want to trade and how much of each asset they want to trade. Those are all parameterized. And you can do that very, in a way, simply or perhaps naively if you're just trying to test things like system robustness to make sure the system doesn't break. But if you start to think about, okay, how do I want to model what people are taking as their information? That may then dictate the kinds of admissible actions that you allow individuals to take, and that itself can be parameterized. And we'll go through that actually in 2 slides, I think. Actually, even the next slide, I think. So it's a good question.
And what about if time is that sort of in a block possible to manipulate flash thinking, front running?
It's possible, right? It's possible that is a strategy of an individual. And so what you might think of as one of your system goals is, for example, to ensure that MEV is minimized, or that there is a disincentive to reordering or front running or other methods of extracting value from the system that goes contrary to the overall system's goal, if that goal is not to provide such value or to use such value as a compensation mechanism for providing the service of mining, for example. Okay. Nice question.
So,
Yeah.
sorry, that's an interesting approach. So that means that if we are looking at event sequence time and we find that empty event sequence that exists within a specific block could open up probable attack vectors or vulnerabilities.
Correct. If you were to, in fact, one of the things that could be done is to examine the way in which the patterns in which you expect to see certain types of activities cluster, and then try to perhaps, I mean, I'm not saying that this is necessarily the system's goal from the beginning, but once you've observed this, perhaps from an earlier version or earlier iteration of a real world application, if you're observing that there are these gaps that are occurring, then you might go back to the requirements or to the system's goals and say, well, actually, you know, we'd kind of like to minimize the chance that anybody can do anything actionable within that particular open space. And so this then gives you this push and pull that, as you remember from last week, the idea of this engineering design process is very much not one shot through and then you're done. It's really going back and saying, okay, well, we've done this testing and now we've identified these gaps that occur. Now we should move back and say, we didn't really know about this requirement, or we didn't really consider it as high a priority as others. Maybe we should now think about the design in such that we can actually eliminate that particular vulnerability if there is one.
Brilliant. Thanks.
Sure. Okay. So just to summarize what a state is, again, the state is the snapshot of the system. It can be influenced by other factors. That's how it's changing. A boring system is one which kind of, if you look at it today and you look at it tomorrow, it looks exactly the same. It's perfectly predictable, and therefore you can feel very confident about your system, but it's probably not achieving your business goals or your system's goals. Things have to change and respond in response to certain things that impact it for it to be valuable. And that's why this mapping F sub t can change over time. And so what I want to do now is to break that open a little bit more and say, well, what are the factors that are most crucial to understanding how the state changes as it moves through time? And we can largely and kind of coarsely divide them into two factors on the basis of how we've defined systems until now, as things that have boundaries with interfaces. We can think of internal factors, such as participant decision-making, if we put participants within our box of the system, as things that are happening within the system that change the state. And we can also think about these interfaces or ports that enter into our system, external factors, such as exogenous shocks that occur to the system, such as a price oracle. If you're thinking, for example, about individuals arbing AMMs, one of the things they're looking at, if individuals who are participating in your system, in their information set, will be likely the valuation of a particular pair of tokens on another exchange. And that becomes that price on the other side can be taken as an external shock to the system, to your system. Now, an open question, of course, is whether or not your system is so well regarded or is in such the public consciousness that it itself is actually influencing the value on the other exchange. And there you have this question of recursion that may occur, and there your system boundary may need to be expanded. But supposing that there is one oracle source of truth, the price of one token for another, and your system is price taking in that point of view, you could consider that as to be one of these exogenous shocks to the system. But irrespective, we use this as a way of dividing up the influences on the state, the things that happen inside the system from the things that happen outside of the system. And as mentioned, each of these could actually be disentangled into things that are deterministic, that actually happen when you see it. Okay, you know exactly what has occurred. Beforehand, you say, okay, this is the things that can occur. Now I know what's happened, versus non-deterministic or random influences, where you can't make any kind of prediction with certainty, but you can posit, for example, a stochastic process. So digging a little bit deeper into each of these, the internal and the external factors, by far the most important internal factor are actions. These we're going to define as, and just use the notation U sub t, as an internal influence on the system's state transition. So you see that U sub t fits inside that F transition function. It still has a little t next to it because of the external factors that can still kick it around. But now we're breaking it a little bit apart and saying, okay, we've got this U sub t, which now is influencing this. This is an action which is now given the state xt minus 1. Somebody takes an action and we get a new state, x sub t. Different actions taken by people give different possible outcomes. And as mentioned, that action can be a decision from a system participant, something that they choose to do. It could also be something which is an automatic response that is programmed based upon different system metrics. And so it's not part of the state itself, but maybe something akin to a controller, for example, that is measuring something, some state of the system. There's a sensor that is taking information, and then there's an update to a particular action that influences the future state, depending upon the measurement's outcome. Now, its action itself may be influenced by the previous state and the previous action, and so we'll codify in a moment how it is that the action has an information set, and that information set, part of the things that are contained in that information set are things like, what's the system look like today? That may or may not be something that people are conditioning on, as well as conditioning on the previous action that may have occurred. And if you think about somebody who's a decision maker, that they probably have some memory or might have some memory of what was done before. But the key thing, and we're going to try to underscore this repeatedly, I think, throughout this, the next, and even the following sessions, is that what is being designed when we design a system through the GDS point of view is not a diktat of what it is people are doing when faced with certain responses. Instead, what is being designed are those ports and interfaces, ways in which actions can be taken. And we call the set of actions that can be taken to impact the system the admissible set. And it's capital U sub T in this notation. And this admissible set is in a way the primal thing that can be enforced by the system on its participants. You can't really enforce a type of person. You can't say, you must be like this, you must be an arbor, you must be someone who's liquidity, looking at liquidity constraints, you must be somebody else. Instead, the system says, these are the things that are possible. And those things can change over time, and you can make it so you understand how they change over time. But what they choose to do from that admissible set is something that is added from the outside. So just to give an idea of what that admissibility criterion looks like, we can think about this as sort of having a pool of possible actions. So there's a state xt-1 that has been realized. It's like the state at the very end of time t-1. It summarizes the system at that point. Conditional upon that, there are a set of actions in this blue ellipse that are possible for, let's say, a user to take a particular action. One of them is labeled here. This U sub T is labeled as being something inside this set. And it's the one that, let's suppose, through some behavioral assumption or some automated response, that this value U sub T is chosen. Now, conditional upon this and the factors of the state update, this allows for one to see possible new actions available when time t comes around. So in addition to having transitions or changes in the state, you also have transitions and changes in the set of admissible actions. In this particular case, we have inclusive actions, which means we've got this sort of Venn diagram where when the state updates, then the union of these is now what you can choose. And things that were previously inadmissible at time xt at state xt-1 are now conditional upon xt and u sub t admissible. So let's suppose now they choose a new selected action, u sub t plus 1. This is coming out of the new values. And then the consequence is perhaps exclusive actions at the end of time t plus 1. So instead of having this whole set available, instead, at the end of time t plus 1, you only have what was left out, what was not part of the earlier set, an exclusive set. And so then you choose another point. An individual user will choose another point from within this admissible set, you don't know which, that will then cause the set to update further into the future. And it's the way in which the set is specified, plus the way in which the set can change, that is something the system is designed by the engineer to fulfill the requirements and the system properties that are of interest. Notice we never choose for people those little points u sub t plus 1, u sub t plus 2. And that's an important distinction to make because many, many, many times in a stakeholder meeting or in a discussion, even at the up to and including the point at which we start to specify requirements, there may have been an implicit assumption about behavior that would have said to everyone, for sure, this is how people will behave when confronted with a particular state of our system. And the problem with that is that, number one, you could be wrong all of the time, in which case you are not simply representing, you're representing what you would like to see, perhaps, instead of what actually is happening. And number two, you may have erroneously based your business proposition upon people's behaving in a certain way. And that can be dangerous, because if you assume what it is that you want to prove, then you put yourself in a position where if somebody comes along and does something differently, or has thought about the system differently and chooses an admissible action from your set of available actions, that suddenly does something you didn't expect and destroys value as a result. Now, that doesn't mean that you can't model behavior. Quite the contrary. What is happening is that you're able to build this set of admissible actions and allow that set to be as richly defined as you like. You could say it depends upon the previous state, xt minus 1. And it may also depend upon, just like the state transition itself, other factors, such as exogenous external shocks. If we think about the individual arbitrageur thinking and looking and seeing this external price oracle, that's something that's conditioned in their information set, may change their action. And then when you want to say, for that given type of individual, there is a potential selection that they are choosing on the basis of that information, what you are doing is describing a selection from the admissible set, big UT, and we call that a policy or a behavior. And it's summarized by this lowercase g, g sub t, tells you for a given state, a representation of the system at the end of time t minus 1 in this case, and what was selected before, u sub t minus 1, you can say u sub t will be chosen out of all of the possible alternatives that are admissible. So again, just to underscore one time out of many to come, while we design in the engineering design workflow, capital U sub T, the admissible set of actions, the assumptions that you need to make to extend into further understanding of behavior requires assuming behavior that is not something that you're designing. So that function G sub T at the beginning of the design process is unknown. Okay, I'll stop here also briefly just to ask if there are any questions or concerns at this point. We're almost home. We've gotten 2 out of the 3 pieces or components for specifying a GDS, a generalized dynamical system. But there is this little bit of a, well, it's not necessarily a subtlety, because the distinction between an admissible set and a selection from the admissible set is pretty clear. But there is this warning, this danger that comes with this, to ensure that when you start looking at ways in which you are thinking about how people are going to be using your system, those are behavioral assumptions that are perfectly valid to incorporate, but must be incorporated outside of the design of the system. Because what you want to do is to test how the system is responding for different behaviors. And those different behaviors will then give you different selections from your admissible set. But you do not want to say that the system is completely contingent upon one G function that you found or that you chose or that you regressed from data even. Okay. Questions or comments? All right. So we got left these other factors, these external factors that are coming into the system. Now, these can affect both the state transition, that function f of t, and the action that's selected, u sub t. And these are things that are assumed to be coming from outside of the system itself. So either a random component or stochastic process, or perhaps an external decision from a non-participant of the system that nevertheless has an impact through an interface. And these factors are then modeled in the system. You can set them up as different types of stochastic processes, as mentioned, machine learning algorithms that are defining for you what's happening, other types of system identification solutions. We've summarized them for the notation of the GDS as Z sub t. And what happens is that if you have admissible actions after a particular point in time, you're no longer saying that there is only one addition to the admissible set following the realization of a particular external factor that is outside of a system, but rather there are many different potential changes in the admissible set that could occur on the basis of this. So as you might expect, it can be fairly delicate if you actually put inside your system an explicit dependence upon an outside factor for what it is people are allowed to do with your system. And in many cases, we start from the opposite point of view, or a stakeholder will start from the opposite point of view and say, I want my system locked down so that external random factors cannot directly influence the system. And that means, for example, that if you need for the operation of the system an oracle, that there are requirements to ensure that that oracle cannot be used in such a way that it actually generates a realization that is feasible, but that you, by modeling or by assumption, thought could never happen, because it will simply be entered into the system, the smart contract will eat it, and it will do what it does on the basis of the value that comes in. Okay. We can put all of this together. This is, again, going to be a little bit of notation heaviness in the system, but it's the last bit of notation heaviness, I promise. What we're doing now is conditioning now on these external factors as another variable. And you can see now that the little t has disappeared from the f function. So now we have a state which is simply a function of the previous state, the action that is taken, and any external factors. And the same goes for the admissible set. The admissible set depends upon the previous state, perhaps the previous action, and again, perhaps upon external factors. And coupling this with behavior, with an understanding of what individuals are doing, or modeling through all of the different types of scenarios or ideas about how people behave in your environment, you can then capture the, let's say, the most reduced form possible of the transition from today to tomorrow, where we use the t to distinguish between these two dates, or from t to t plus dt in a continuous time environment, or from event t to event t plus 1 in an event sequence time. And that looks like this. All this is saying is, I've got a state transition, I've got an admissible set, I can put those two together using one or more different types of G functions that themselves can be based upon the previous state or the previous action that was taken or other factors. And I can reduce this dependence and just summarize all of it. And we summarize this with another mapping, which we call H. And if H depends upon previous states, actions, and outside factors, then it's dependent upon all three just in the same way that the state transition function is, and it acts as the state transition map. And in the simplified, most simplified environment where everything just depends upon the previous state, then we have a first order transition map of the GDS. And once we've got to this stage, we are able then to take all of this nomenclature and all of the ways in which the system is now represented as changing over time from these factors, from identifying the boundaries, the context, the interfaces of the system, and therefore identifying things that are inside versus outside, and put this all into one particular mapping that we can take and use as a blueprint for a computer implementation. And this is the specification of the GDS environment. On the left-hand side, which is not particularly useful, but I thought I would give it to you for the sake of completeness. This is simply some of the notation that we've been describing. We do tend to update this just depending upon the clients that we are interfacing with, and so we have a few different versions of the basic definitions floating around. Michael Zargam and I are in the process of, and it seems like we're perpetually in the process of writing down this for as a paper to try and get this out to a wider audience. So stay tuned. Hopefully we'll be able to do that in the next few weeks. On the right-hand side, you have a nice transition diagram which gives you the way in which information flows are occurring, conditional upon what you've just seen in the slides. This is just another way of seeing the same thing that you saw in the equations, giving the way in which a specific kind of agent behavior summarized in that G function can influence the system. And I think this will be referenced again when we move into the mathematical specification session next week. Okay. And just finally, to place this within the context of what you have seen before, last week Barlin put this up in the notion of how do you view the system from? Where are the different ways in which people have as their point of view, their source of understanding of the system? We have this triangle between the designer's model, the operator's model, and then the actual system itself and how that changes over time. And just to place where GDS is within this context, it's here. It's in the abstraction and formalization side of things. So this is actually the way in which we can start to build the different pieces of what you're going to be seeing over the next few sessions within this type of models as views environment. It is the most abstract part of this approach, but the reason for it is again to make sure we have that balancing between the complexity, which causes things to, you want things to be more abstract as you have more and more complex things that you're taking into consideration as changing over time. But at the same time, always with an eye to how can we implement this in the computer system? How can we do this such that we are able to get testable restrictions for verification of system properties? And so that's where this this component of that engineering design process fits.
Question.
Yeah.
So is it possible that these factors such as U of t and Z of t could have like a confounding effect to create a null state, wherein it would just simply crash the system, or system wouldn't exist at a point in time? And how do you determine that? I mean, just
Yes.
curious, that's all.
No, that's an excellent question, because that is, of course, one of the reasons why you are thinking about requirements as becoming critical to what the stakeholders want. The stakeholders, for example, don't want the system to crash, right? You may think, for example, just to go back and use the Bitcoin as another reference point, you want no double spending to exist as part of the underlying system. You don't want some combination of individuals' activities plus a particular kind of random influence from the outside to adversely affect the system such that that double spending can occur. And of course, that requirement of no double spending, it has a particular limitation, right? You can only get up to the 51% attack, and then the system does in fact lose value. So it's a known feature. And so then as a stakeholder, you have to sit and go, well, okay, is it worth the trade-off? Is the likelihood of this failure low enough that I'm willing to take the risk? Or to put it differently, and for those of you who have kind of this risk assessment or risk management background, is the value at risk? Is that high, too low? At what confidence interval? At what significance level am I assessing that risk of value? And those become the key determining questions.
We do something known as frequency of occurrence. So
okay.
Yeah, that's an interesting parameter that we use for generic processes and systems, but that's a different.
And so it does the same thing. I'm assuming it attempts to try and map out the types of things and the likelihoods at which they will occur and the losses that may occur from each.
Definitely, yes. Yeah.
Excellent. Okay, any other questions? Okay. It's a lot to digest. Because of its abstraction, you can get lost sometimes in the weeds a little bit. What we're going to do is come back to the idea of a GDS. And I think in particular, we probably will leverage within the class of AMMs, the notions of business requirements as symmetries, which is to say that there are conserved properties of the system that occur as part of the business requirements that you would like from many different types of AMMs, from classes of AMMs. And these imply different types of mechanisms that you then model in the abstract framework for the state transitions, build a blueprint of what goes in, what comes out, and how, and then design candidate mechanisms within the system that change that state. And so when you look at that F function, that F sub t, built into that are the design decisions of, well, what kind of swap mechanism do I want? What kind of add, remove liquidity mechanism am I dealing with? And building and designing those will take us forward to the end of the sequence. But before doing that, I wanted to at least highlight for you in the code one example of following through one state variable and showing you one set of transition functions and showing you one set of user actions. So again, working from both sides, I can give you kind of the high level theory, but it's sort of high level theory. But at the same time, having something in the code to look at can often help fix the idea of what the abstraction was and give some ideas on the rest of the code, for example, and also what it means to have a blueprint. Because the blueprint, in a sense, is the missing piece. You can't easily go from a GDS specification directly to code. There are many people who can do it. They have a mental map immediately. But for most people, and even those individuals, I think when pressed, would admit that they have built a blueprint as a result of what they have seen and thought about from the GDS or from the dynamical systems point of view. And so that's the point of where we'll be going next week in Barwin's session on math specs. So just to give you a teaser on coming up from below from the coding side of things, it's interesting to think, of course, the questions or the raison d'etre for our core sequence has been the Hydra liquidity subsystem. So what does it look like from a GDS perspective? Well, the thing that I would like you to take away from this lecture and also from the assignment is to identify different components of the GDS framework. And then if you want, take a crack at sort of understanding what might be business requirements or goals associated with them. But at the first blush, things like identifying the system states. What is a sufficient statistic to tell you what the snapshot is of the Hydra liquidity subsystem at a point in time? Then identify things like the admissible action sets. If individuals are coming into the system, if you can categorize them as two types, say a trader and a liquidity provider, what are the admissible action sets for each? And finally, identifying, and this of course is the crux of the mechanism design question, identifying the transitions from one state to the next. Where is it the transitions are occurring? How are you getting from your one sufficient statistic that you identified as a state to its representation some point in the future? And you want, of course, to take into consideration things like the admissible action sets, also things like exogenous factors, external factors that may be influencing this. And so you're going to see a version of this slide at the end of the lecture today, which is the assignment. But this is just to kind of give you a summary. And of course, you can do all of this formally once you have the blueprint in hand. But what we'll do is look at it within the cadCAD implementation. And so just to give you a brief summation of what we're going to see in the code in just a moment, what we're going to be examining is one particular state of the system. So there's one component of the larger state of the system. It's treated as a state from the cadCAD side of things. And we'll just take this to be the base token amount, the amount of HDX in the system. It has a variable name in the cadCAD code, if you haven't seen it yet, of capital Q. And we're going to take it as an example, internal factor, the user action. And this user action is inside a function called the action decoder, which we won't delve into today, but we're going to examine the consequences of the action decoder in the mechanisms. Essentially, it's saying what's an admissible action for an individual, and then we're going to associate with that admissible action other attributes or features like how much, if a trade is admissible, how much of a trade can you do, or which asset is traded. That will be the internal factor. And then we'll have some transition functions that we can examine. When a swap between assets is performed, there's one function name. We'll also look at the swap between an asset and HDX. There are two functions for that, one for which you are actually selling in and one in which you're buying out. And finally, the add and remove liquidity mechanisms. And so each of these are acting as transitions of the system just with a lens or with a view toward the state of the system of the base tokens amount Q, the amount of HDX. Okay. So let me stop this share, and then I'm going to start a VS Code share very quickly. Hopefully that will work. Any questions before we jump into the code? Okay. Let me grab this. Okay, can everybody see the VS Code window of the partial state update block?
Yep.
.py. Okay, very good. So you've probably already moved and kind of taken a gander, depending on your different level of familiarity with the cadCAD environment, into the partial state update block or the psub. This is where the transitions, the state transitions are defined and where the admissible set updates are defined. What we're going to be examining is here in the Hydra world, the variable, which is the base token amount Q. Now that has a particular location where, conditional upon the action taken by an individual, the internal action that's available as part of the admissible set, a different updating mechanism is performed for the state of Q. So you can think of Q as sitting there as your xt minus 1. And then the function, the mapping f sub t, is actually many different functions. In this case, I think 5, depending upon that u sub t. So if somebody says, I want to swap, well, that's a selection of one particular admissible action, u, and it leads to one particular realization of that f sub t. And we'll see that in a moment. One for add liquidity, one for remove liquidity, and so on. And within those discrete choices, swap versus add remove, there are decisions that can be up to the resolution of what is allowed as a trade, can take many different values, like the amount of liquidity added, for example. You could even abstract that in your GDS as a real number. And of course, here we would granularize it to what we can do with integers, but allowing sufficient resolution to allow many integers. And so there's a large admissible set, for example, for the amount to come in, and that then constitutes another part of that admissible set, u sub t. So as you're looking through the code, think about viewing each of the types of variables and their impact on the system as falling into these different buckets of summarization of the system in some capacity, in this case, the liquidity of HDX, and then user actions and how those user actions are affecting transitions. And finally, user actions within those user actions. So conditional upon one action being taken, are there other attributes that are part of the user's admissible set, such as trade size or trade direction? And that will help to build why it is, ex post, of course, why it is that cadCAD is, in fact, the reference implementation framework. It is actually a representation of a GDS system. All GDS is representable in cadCAD, and things that are in cadCAD are representable as GDS environments. Okay, but let's jump into this very quickly in the time that we have, just to show you, once you've decided to, inside the variable update, the state variable Q, when it is being asked to update itself in a time step, it dispatches to this mechanism hub function. This mechanism hub is where the first of the different choices of users in the user admissible action set are being parsed and are being placed into different buckets. There's one which is, I want to buy the risk asset by swapping for HDX. I'm putting HDX into the system. I want to take HDX out of the system in a swap by bringing in, by selling. Sorry, so this is buying the risk asset by selling HDX. This is buying HDX by selling the risk asset, and these are both swaps. Then we have adding liquidity, removing liquidity. And finally, we have two assets that are being swapped. So these are all the partitions of the admissible actions at the course level of, this is what I want to do with the system if I am a trader or if I'm a liquidity provider. So for example, in the mechanism that is being presented in the code, there is no change in the state variable of HDX when two assets are swapped for each other on the other side. So you have two tokens, they are swapped one for one. This is the mechanism that is then referenced. And you can see the nice thing about cadCAD is that it provides you with all of these different values of the state of the system just at the end of the last time step, all of the xt minus ones, as that's in previous state, as well as policy inputs, the things that have been done in the past, individual decisions that have been taken, those sort of second order admissible action values, like the amount of a trade, for example. And you can see what this function does. It says, give me what it was before the value of HDX and return it. In other words, the transition function, when you have a swap for HDX, doesn't modify the state at all, or rather it returns the same state as it was previously. Now, if we move to, let me buy a risk asset by giving HDX, well, of course, you can see intuitively, yes, the amount of HDX will change. It has to change. You're putting it into the system. How it changes is, again, a mechanism that is being derived and defined. And you can see here that if you want to understand what is being placed into the system when somebody is selling HDX into the system for a swap, well, all you're really doing is adding whatever people are swapping into the system. And here you can see there's no fee for on HDX that's being taken out at this point. There is a sanity check. Of course, there is a requirement that, if nobody is actually swapping anything, well, then just return the original state. Or if it turns out that they're attempting to put in or take out too much of what's there, then return the original state. So you can put controls in, sanity checks into each of the systems as you are investigating whether the systems are valid. And part of the mathematical specification will make this explicit, what was implicit in the GDS framework, the domains and the ranges of each of the variables. We can look also at the purchase of HDX. And here I've changed a little bit of the code relative to what you have seen, not in terms of content, but in terms of spacing. All I did was collect different variables into different categories just for today, for the lecture, to show you how they're parsed out. These, anything with the policy input, are things coming from the admissible set for the actions. What asset is being entered in and how much. The pool, the state of the pool is actually a dictionary that's capturing different facets of the asset pool in the system, the reserves, and a technical coefficient that we're going to get into when we start looking at the symmetries we're trying to preserve in the system. And then we have the states, the previous states of Q, and another helper state that we'll look at also later on. We again have some sanity checks to make sure that we're ensuring that things are actually happening when the swap is occurring. And then down here, you finally have a mechanism, something that says, if you sell a certain amount of an asset, and that's here, a certain amount of an asset into the system, this is the amount of HDX you get back. And then you return then the mutated state of the system. That's the state transition that occurs in the system. And you'll notice that I've parsed these out so that we put all the policy inputs here, the state variables here, and then we have this leftover guy, params, a parameter. This, harkening back to the earlier question, describing how do you parameterize external events? Well, you can just as easily parameterize the system mechanisms as well as external events. So not only can you draw things from particular random distributions, but you could say, look, we actually have a class of mechanisms, all of which, each member of that class of which fulfills our requirements. But there are other requirements where different values of A will impact those particular requirements differently and change system goals. And part of then the Monte Carlo process, that process of generating scenarios or ensembles, is to actually look and find over a wide swath of different A values, that A value or subset of A values that meets or achieves particular system goals as represented by functions of key performance indicators, or KPIs. So you measure the efficacy of how well different system goals are being achieved for different values of A. And by doing so, and putting that together in a consistent fashion, you are able to claim that there's a subset of values of A for which the system goals achieve some threshold criteria of acceptance. And in the last lecture that we have in the sessions, parameter selection under uncertainty, well, when we're talking about parameter selection, we're talking about selecting that parameter. And if you were thinking about this environment, augmenting it, for example, in a fee-based system where we have dynamic fees that are introduced, which currently aren't part of the system, but can be, having a fee structure which is sufficiently broad that itself will probably have one or more free parameters that will be just like this one to be selected from different ensembles of realizations. So in a nutshell, we can see in this particular mechanism that is being highlighted, the way that GDS is operating. Perhaps it looks behind the scenes, perhaps it seems like it's a bit of a stretch, but it's actually a fairly good one-to-one mapping. We also see how the requirements and the system goals have been encapsulated in things like the sanity checks and in the mechanism, in this case, the swap mechanism that was designed at this point. And finally, we see where cadCAD can assist in closing the system to find how do we get actual verifiable metrics that we then use to assess alternative characterizations that the GDS framework is more or less agnostic to a particular value for this parameter. Okay. We have a few more to look at, and one of them is adding liquidity, but these will now become more or less the same theme, the same feeling for each of them. Again, that A parameter does enter into the process. Here again, we have the user admissible actions, what asset they're adding liquidity to and how much. And just as before, in fact, the same variables as before, we have the previous state of, for that particular asset, its amount and its technical coefficient, which we'll look at for the requirements. And from doing this, we actually end up with a whole swath of different updates, state transitions, but this particular mechanism then of that takes the final, the apotheosis of these updates and says that's the difference Q plus, which we call delta Q, and a different part of the code is called Q plus, is actually delta Q plus Q. It's called Q plus here. The math is simply a little bit simpler because it's a multiple of Q. But this is now XT plus 1 given XT, or XT given XT minus 1 in the add liquidity mechanism. Again, because repetition is our friend, the remove liquidity mechanism looks very much the same. We still have the same kinds of distinctions. However, you'll notice here, there are other values that are now important to come into the system. And these, again, are states. These are part of the entire state of the system that is being derived. The price of the asset and the share of the entire share weight of the asset itself is also used in the computation of the new value for HDX. So we see that liquidity events, and it makes sense, right? Because remember how the Hydra AMM works, you want to always have the amount of HDX reflecting the value of the rest of the assets in the pool. So anytime you add more assets to the pool, well, you have to change that value. And you want to change that value in such a way that certain system goals are preserved. And that's what we're seeing in this environment. And it's, again, a one step forward, look forward, where we're seeing this kind of GDS framework where, conditional upon the current state, we move forward to the next state, given external factors and internal factors such as the admissible set.
One question here.
Sure.
I see here that a liquidity change only seems to influence one variable of the whole state, and I'm a bit where goes the other asset? Because
right. It's a good question. This has to do with the structure of the way in which cadCAD updates variables. So here, if we go back to the partial state update block, you will see that for every state, there is a dispatcher for each of the actions. Each of these gets updated according to different conditions, such as liquidity events. And so you can even get a hint of that inside this. Let me go back to this very quickly. You can get a little bit of a hint as to where you're going to see updates, because these are updated, R+, CI+, and Y+. Now they're just helper application. They're helper variables to compute in the end this updated state here. But if you go in and look at the way in which the system is updated, according to when an add, in this case, a remove liquidity event is occurring, well, you're going to see changes in these variables as well.
Okay, that answers the question. Thank you.
Yeah, sure. And it is something to drive home that there is an explicit mapping for each state variable component in cadCAD, so that what you are seeing is in some ways a duplication of code, because we saw those helper variables being computed. And so you would say, well, why don't we just compute them once? One of the reasons for that is to ensure we have a consistent state, so that we're actually doing this state updating, so that we don't actually overwrite a previous state with an updated state and then overwrite that again with a new state coming forward. So there are some consistent.
So you're kind of recreating a functional environment with no side effects.
That's right. That's
okay.
And that's the better way to describe it from a coding point of view.
Okay.
That's right. Avoidance of side effects is the key here. It is sometimes more art than science. I will defer for sure to Barwin on some of the more arcane solutions that he has found over the years to ensure that side effects are eliminated, and if not eliminated, then understood, so that we can be leveraged or minimized. But that is indeed the reason why. Yes.
Thank you.
And finally, I think we have one to go. Oh, sorry. Was there another question? Okay. We have one last one, which is just the exchange of two swap assets. Oh, we did that first. That's right, indeed. And there's no change in the state because the risk assets do not change the set of Q. Okay. So hopefully that gives a way of tying something very abstract to something very tangible. And what's missing, of course, is this way of saying, if you were someone who is going to code this, you wouldn't hand them a GDS. You wouldn't hand them and say, here's the dynamical system, go to it. What you would instead do is say, here's the blueprint. Here's the way we can distill what a GDS framework is showing into something that you can hand to somebody who will then code it. And they don't have to code it in cadCAD. They can code it in anything. But the key thing about cadCAD is that it is a framework for representing GDS, Generalized Dynamical Systems. And even within the context of cadCAD, because it's a framework, we're seeing one particular implementation in Python, but there are others. And in particular, there are other languages that it's currently being worked on. Julia is at least one of them. So you can think of cadCAD in a much broader framework as the mechanism by which a blueprint is implemented. And then the choice of programming language, in a sense, comes down to fulfilling other requirements or other constraints. Okay, let me then wrap up here with a summary. Okay. Any questions before we wrap up with the assignment? We could leave it to a Q&A toward the end after we've finished up. Otherwise, I'll just proceed to kind of give you, as a wrap up, the thing to do next. So that we saw as initially in the goals in the introduction, the idea that following the completion of this explication of what a generalized dynamical system offers and why it's important to formalize, how that formalization can occur, the next logical thing to do is to say, well, I have defined a system. What is it that I'm looking for when I want to think about how to put this into a GDS framework environment? And it's a difficult question sometimes to understand what it is that is summarizing a system and how that system is changing. And in particular, that hidden thing always in the back of one's mind, am I assuming something that I really shouldn't be assuming? Am I actually assuming something about behavior, about that G function that I shouldn't be assuming? And so the assignment is really just to identify those pieces in the same way that we were identifying them and for that particular state variable Q in the code in the cadCAD environment. So for your system of interest, look for the states. What is it that provides the snapshot of a system at a point in time? And what, if any, are the restrictions on the states? Those restrictions often come in the form of domain and range restrictions. And so you may want to be looking and saying, well, what do I want those things to have allowed values for? What are my technical constraints that prevent me from modeling a system with this state, which I think is great, but it just turns out that thinking ahead, if I'm ever going to put that or code that in Solidity, I can't, for example, do it in that way. What is it that I need to think about as a defining restriction that might occur? Then think about the internal factors. What are the decision makers' actions, and what is it that you are allowing participants to do in the system? If you have a particular part of the system that is an auto-regulator, what is it that the regulator is allowed to do when it takes the state of the system and then provides something that then changes the new state? Even if it does that automatically, it's still part of that admissible set definition. So you want to think about the admissible actions that can be taken within the system. And finally, the external factors themselves, the exogenous shocks, the price, the oracle prices, other things that you are thinking of as explicit interfaces that go through the system boundary into the context that you have found interesting. And say, this is a necessary input into the system, or if not from a business point of view necessary, you see it's unavoidable from a technical point of view or from a behavioral point of view, that this type of thing is going to have an impact. Identifying those is very useful because you often can think about, if you've been having some difficulty on drawing that system boundary or defining those interfaces, looking for exogenous or external factors often helps to clarify and say, okay, I remember, yeah, that's for sure not what I care about, but that's probably going to be interesting. So I'm going to have that be the external factor. And oh yeah, it's going to come into my system this way. And therefore, I think it's important to make sure that that interface is defined. So you can get some recursion back to the system definition itself as you're thinking about these different components. And finally, once you have all three, how does it change the state? What's the update? What's the state transition? Sometimes called the state mutation. How does the state mutate in response to these different features for your system of interest? And once you've got that, you're ready to proceed really to the next step, which is defining this blueprint and the mathematical specification. And what we'll see next session, I believe most likely, almost surely, for Barlin, is that there will be two types of blueprints that are produced, usually in our design workflow. The first one is called a concept math spec, and it simply looks at what is feasible versus what is not feasible in the system. It simply says, what are the restrictions on domains and ranges and on the way things compose to each other that the GDS framework implies? The second one is called a preliminary math spec, but in fact, it's the working mathematical specification blueprint for the cadCAD implementation. That one actually then posits different specifications of the requirements taken from the GDS environment into actual, in this case, formalisms. So updates that really do occur, those equations of the Q plus that we saw in the code. Those are the mechanisms that are being designed. And so that part of the system then is encapsulated once you've looked at the conceptual framework. And the reason for this distinction is because it often helps to inform how well has the GDS matched the preliminary, the concept of the mathematical specification to inform the mechanism design that goes into the preliminary math spec. And then once you've got the preliminary math spec, you use that to code into some reference implementation that can handle a GDS environment, a GDS transition system. So that would be the rub of the assignment, and that way you're in great shape then to move forward to the next step for the math spec discussion in a week. Okay, questions, comments? So that assignment, of course, is going to be in the slides. The slides will be updated, uploaded today into the drive. Pass them on to you.
Yes.
Sorry.
Okay, you go.
Thanks. A couple of comments. I think this is very enlightening and a brilliant perspective to have when looking at a systems design. One of the other questions I had in mind was, how do you look at the KPIs which are externally defined and not intrinsic to the system? For example, in my case, I'm looking at regulated assets, and there are certain KPIs which are defined by the regulator to protect the interests of people. So will that then start becoming an external requirement, or is it something that I need to model across, throughout my systems. Just a perspective that I'm trying to build.
It is in the end a requirement that the system has to fulfill if it is something that is whose binding constraint, if that constraint binds, causes the system to not function. So for example, if it is actually a law and your system generates something that breaks a law, then the outcome of the system being shut down by the authorities would be a negative outcome from that requirement not being fulfilled. So the externality or the external or internal nature of the requirement is different from the assessment of the systems from an internal or external point of view. In a way, that's the business requirement telling you that the system as a whole has to have this minimum threshold of a particular metric that you've chosen, which is that it has to be compliant, let's say.
Okay.
Yeah.
All right, that's useful. Cheers. Thanks.
Sure.
Yes, I wanted to ask, maybe after some time in Discord, you could share some resources about GDS, and so before doing the assignment, if we want to learn more and find answers to questions, so just some resources, and even into the more technical side of things, for example, like understanding the mathematical equations you showed today, to just better understand some resources.
Yeah, no, I can. I will pass on. How about I put this into the Discord channel? Some just general references on dynamical systems, which may be helpful. For GDS is something that we are trying to codify our knowledge into a workable document that can be used. However, we've done this partially in the minimal specification of a cadCAD model. There's a README doc at the beginning of this minimal specification that has actually pieces, a little bit of what we've been describing today, plus how parameter selection occurs using that point of view, that I think would be very helpful, because it retains kind of the same level of detail, but also is another view on this from the point of view of what constitutes a minimal working cadCAD model. And so I'll place in the same topic the URL to that minimal specification.
Yeah, that would be helpful. Thank you.
You bet. Other questions or comments? We have about 20 minutes or so of time.
Yes, maybe one, let's say, combined question comment. Has anyone thought about coding similar systems with Haskell? Because there we would definitely have a functional language without side effects. So why is everything coded by everyone in Python?
That's a good question. There's two questions, actually. I think to answer the first one, I think that the way in which the expertise has fallen to date has not had one or more individuals of the team within BlockScience coding up a Haskell variant. There has been a lot of work on performance improving the speed of the Python implementation. There are a couple of different flavors out there. I think one of them is called RadCAD. Another one is something that is using Cython to try and precompile some of the more primitive operations. But the second answer is why Python? Because it is the minimal meeting at the middle of the technologies required for people who are thinking abstractly and want to code, and data scientists who are looking at data and want to understand. And so I think if you look at it through the lens of people who are taking real systems and trying to use the resources that Python makes available for exploratory data analysis, for machine learning, it's kind of a one-stop shop for that on the one side. On the other side, traditionally, and especially coming from academics, for those of you who've seen this and come from this before, MATLAB has been kind of the de facto builder for systems analysis, or even
yes, or Mathematica from Wolfram.
Mathematica for the abstraction layer you can do for sure. And so you could use, for example, Wolfram Alpha to do quite a lot of the derivations of particular mechanisms, for example. And the reason that it has not been something that we have used as an assumption of what people have access to is simply the barrier to entry. The barriers are just, they're just extremely high. There are benefits to being in a gilded cage. Everybody who owns an iPhone, I think, knows this. But when you are looking at ways of extensibility, when you're looking at the primal focus, for example, for cadCAD to remain always open source and then be able to be iterated on and expanded on, it does not mean that people should not use MATLAB. It just means that the accessibility barrier is extremely high.
Thank you.
Sure. Other questions or comments?
Well, then I can directly follow up.
Sure.
Some days ago, I have given a small presentation on thermodynamics, especially Hamilton and Lagrangian formalism, and I'm quite sure that some of these formalisms is already used in generalized dynamical systems. How far into physics has this already gone? Do you know about that?
I would say probably very far. It may not be defined in that fashion. Just to give you a little bit of the historical backstory for GDS, this was articulated first in the it was articulated first in the mid-1930s, where people started to think about how would I, instead of having a differential equation give me one rate of change, how would I make it a set of possible changes? That's called the differential inclusion. This was followed on in the 1960s by work from Roxin, R-O-X-I-N, and he actually titled from a pair of papers, titled one of them as Generalized Dynamical Systems with Contingent Derivatives. And so what he was doing was building essentially the set valued framework for allowing the transition, that F function, to be a set. So that instead of knowing absolutely for sure how the system changes over time, you would actually see how the system's set values would change over time.
State
now,
transition system, that is.
Yes, exactly. So it'd be a set-based transition. That's right. And so I think this has been done in physics for many years. There are, of course, lots and lots of machinery and especially from if you're looking at the systems ensemble, trying to make it as Markovian as possible. And once you've made something Markovian and you've defined how the system is being updated conditional upon a set of parameters in an information set, whether that information set has a lot of structures like a sigma algebra, or whether it's something which is being updated only infrequently, I think probably most physicists would, and yourself probably, when confronted with a GDS, would say, oh yes, I know these systems, but it may not have been.
It looks quite similar to the things I'm working with, yes.
Yeah, it just may not have been contextualized in that fashion, and it may not
exactly
have utilized the same tools. Yeah, one of the nice things about this, I think that will become apparent, and I think I caught a little bit of this just now in the Discord, is from your conversations before, is this notion that once you have specified the GDS and that next step of specifying the mechanisms, that introducing symmetries into the environment from which you can derive conserved properties, which is something that is, of course, used heavily.
Yes.
Yeah, this is something that is possible to articulate within a GDS framework. So you don't lose resolution by attempting to introduce symmetries, and I think as Colin had mentioned, hearkening to Noether's theorem to ensure that.
Let me guess that the symmetry comes in as an eigenvalue problem of the transition matrix.
You could.
Okay.
Yes, that's one particular transition that would occur if you can generate the system such that you have an eigenvalue decomposition that is feasible. Another way to think about that would be to look at the, let's see how I want to say this. You look at the structure of the environment such that the kinds of trajectories that you are imposing on this has a symmetry from what is called a Lie group. perspective. So there's either lead transformations of the systems that can occur, and those two, you can lean again on Noether's theorem, which is great. I mean, and then try to identify the set of symmetries that can be represented by a conservation function, which we call an invariant function for many of the AMM systems. And there may be, I don't know yet, but there may actually be a way to go back and forth both ways. Because that's kind of the holy grail would be to say that for every AMM or for every class of GDS, even better, there exists a set of symmetries such that you have these sets of invariant functions with conservation, with conserved properties, that you then have to go and explore the exact case that you're looking for to actually articulate further. But that general existence proof, or that general existence formulation,
difficult, yes,
great.
But there's quite an overlap with gauge field theories of physics, directly formulated on Lie groups. So it's quite fascinating how
this would be
how one meets
my,
at the same points coming from wholly different directions.
It would be beyond my bailiwick, but I would be very interested to hear kind of how that transpires. And of course, I would try my best to kind of monitor the Discord over time. I won't necessarily be able to answer with everything, so my apologies in advance. But it sounds like you guys are already thinking along the same lines, and hopefully today's lecture kind of helps at least provide a context.
Absolutely, yes. Thanks a lot.
Great, sure. And parenthetically, for the rest of anybody who has never seen this stuff before, do not feel that this is anything that is taking as a prerequisite moving forward. It really is about just thinking about the system you find interesting and thinking about the part of the system that doesn't change at the beginning when you say that's what the system is. Well, that's going to give you a hint as to what the state is. If you say, well, what would it look like if I close my eyes and then open my eyes a little bit later? Oh, it's different. Why is it different? Well, that's going to give you an impact and understanding of the internal versus the external factors. And that's really the building blocks here. So you don't need necessarily to delve into, if you've never seen it before, lots and lots of pieces of machinery. And of course, I'll provide some resources for further reading on dynamical systems, at least in the Discord. But the real idea here is to say, why is it that I can actually go without actually knowing GDS and code something in cadCAD and it works? Well, the reason is because cadCAD is following these laws underneath. And so as you work through cadCAD, if you know what cadCAD is doing, what you're doing is really opening and unveiling these layers of consistency that the GDS framework has provided. Okay.
Very cool. Yeah, not from me, but any final questions? Seems like we're getting to the end here. Cool. Yeah, then I think we're all good to wrap up. Anything left from your side, Jamshid?
No, not from my side. Thanks very much. Been great questions, and certainly looking forward to the Tuesday session, which I'll be there for at least part of, for any questions for the assignment, and of course continuing on through the next sessions and beyond. So thanks.
Cool. Great. Yeah, this was an awesome lecture. I think everybody is still mulling it all over. It's awesome to see. Cool, and great questions, everyone too. Yeah, then that's it. We will give you 12 minutes of your day back. Yeah, thanks again for coming, everyone, and we will see you on Tuesday for the Hack and Share.
Cheers, Jamshid.
Thanks, everybody.
Cheers, bye.
Cheers.
Bye.
Bye.
Thank you, everybody.
See you.